Welcome to Algebra 1, Unit 6, Lesson 6.3, Applying Linear Equations. Pearson, Algebra 1, copyright 2009. I'm Mr. Polarski, and our objective today is I will be able to interpret linear graphs. Key word in that objective is interpret. We're going to learn how to read a linear graph, interpreting what the labels and slope and y-intercept mean. When in the first example we're going to do today, these two key words, continuous and discrete, I meant to put continuous data and discrete data. There's a difference between these two. Continuous data means that you can have parts of a whole represented, either fractions or decimals, whereas we're going to would need to use a solid line to represent that particular situation. When you have discrete data, only whole numbers make sense. You can't take parts of a whole. We'll see an example today using discrete data. The other pair of keywords here are independent variable versus the dependent variable. That really has a lot to do with the first example, where we're going to be creating a graph that could be interpreted. So let's get on with the lesson. You can model many real-world situations with linear equations. Recall that the graph of an equation shows the solutions of an equation. However, for discrete, real-world situations, not every point may represent a reasonable value. So there's one of those key words, discrete. Not every point may represent a reasonable value. A lot of the times that means for discrete that we're not going to be allowed to have parts of the whole, such as if you're buying something. You can't buy 1.5 bottles of pop. Either you have to buy 1 bottle of pop or 2. You don't buy 1.5. So in that case, the data would be graphed as individual points, not a continuous line. Example 1T, RealWorld Connection. A health food store has 15 bottles of one vitamin in stock. The manufacturer ships these vitamins in boxes of 20. Write a linear function that relates the number of boxes to the total number of bottles of this vitamin at the store. Graph the function that models the situation. Well, we just read the problem. Now we need to interpret the problem. First, you want to identify what's being asked for. And what's being asked for is normally at the end, not always, but normally it is. Graph the function that models this situation. So we need to create a graph. I have a coordinate plane right here. I'm going to show you how to set it up in this lesson. So ultimately, we need to create a graph. To create a graph, we need to be able either to come up with a table of values or an equation. And it tells us also to write a linear function that relates the number of boxes to the total number of bottles of this vitamin at the store. This sentence gives us another objective that we have to complete. We have to write an equation, then create a graph. So to do that, we need to write the equation, we need to identify the independent variable and the dependent variable. Before we even do that, we need to identify what is variable in the problem situation. I asked this question in class, what's the variables? One student told me 15, another student told me 20. It makes sense that you'd want to say, this is a math problem, so I'm going to give the numbers as the answer. It might be right, but they're not. What's variable is what we're going to use the letters to represent in our equation. In this sentence here, decoding this sentence in this problem, we write a linear function that relates. Right here, when it says write a linear function that relates, what follows that word relates are the variables. We're going to relate the number of boxes to the total number of bottles. I'm going to shorten them down, but that would be the total number of bottles of this vitamin at the store. So we're going to relate the number of boxes to the total number of bottles. Now, we have to decide which one of these is the independent variable and the dependent variable. You want to ask yourself, does the number of boxes depend on the total number of bottles at the store, or does the total number of bottles at the store depend on the number of boxes? A key word to determining the dependent variable is this word total. Normally, typically, When you're finding the total, that's the dependent variable. So identifying the dependent variable, the total number of bottles at the store depends on the number of boxes that are ordered or the number of boxes that are in the store. So the dependent variable in this case is equal to the total number of bottles. Now, on the note packet, if you're watching this for my class, these words independent variable and dependent variable aren't there. You're going to want to pause the video to write those in because that's an important concept in creating the graph. So the independent variable is the number of boxes. Now that I have the independent and the dependent variable identified, I'm going to label my x and y axis. The horizontal axis, or the left and right axis, is always the x-axis, and the up and down axis is the y-axis. When we're writing equations with x and y, the independent variable is always x. The dependent variable is always y. So now we know along the x-axis we're going to graph the number of boxes. And along the y-axis, forgot my e in here, the number of boxes, and along the y-axis we're going to graph the total number of bottles. Now, I didn't really leave myself much room, so let me fix this real quick, make that a little bit smaller, give myself some more room. Along the y-axis, or the dependence axis, we're going to have the total number of bottles. I'm just going to write the word total to save myself some time and some heartache. I have a hard enough time writing with this thing when I make these videos. So that's what's going on. We defined our variables and we started to set up our graph. Now, we need to number, well, first actually I guess we should write our equation. When writing the equation, you want to start with the dependent variable. Now, y in this case represents the total number of bottles. When I write this equation, I go back to the first sentence. A health food store has 15 bottles of one vitamin in stock. So the store has 15 bottles of the vitamin. So that's a part of the total. We're going to add that to 20 times x. Now, the 20 times x, where that comes from, is from the fact that if they order boxes, they're going to have to order boxes of 20 because that's how they come shipped from the manufacturer. We have to multiply that by the number of boxes that are going to be ordered, whether it be 1, 2, 3, or 4. So this equation here relates the number of bottles in the store to the number of boxes that have been ordered. Now, a reasonable thing to do would be to make an XY chart here. Now, I just taught my students how to use the TI-84 graphing calculator to make a table of values from an equation. A reasonable domain or reasonable set of X values here would be 0 boxes, 1 box, 2 box, 3 boxes, and we could do more if we wanted to. So labeling the X-axis 0, 1, I put that in the wrong place. That should be shifted over here. The 0. The y-axis is the 0 line. 0, 1, 2, 3. Now, I find my y values, or my range values, by substituting 0 in for this x. So when x is equal to 0, I substitute in y is equal to 15 plus 20 times 0. Doing the math on this using the order of operations, 20 times 0 is 0, plus 15 is 15. When I substitute 1 in, I would just change this x is equal to 0. I change to 1, and this 0 would change to 1. So then I do the arithmetic on this. 20 times 1 is 20, plus 15 is 35. So that would give me the next value. I think I said 25. I meant to say 35. And again, we would change this 1 to a 2, my next value in the table. So when x is equal to 2, I substitute 2 in for x. 2 times 20 is 40. 40 plus 15 is 55. So that would give me the next value. And the value after that would be with the 3. Changing that 2 to a 3, substituting the 3 in. 2 times 3 is 60, and 60 plus 15 is 75. So on my y-axis to number, I need to go basically from 0 to 75, and I think I'm going to count by 20s. We're going to count by 20s. So this would be 20. Of course, this would be 0, 20, 40, 60, and 80 here. So then we need to plot the points that we just came up with. 0, 15. Now, halfway would be 10, so 3/4 of the way would be 15. 1 and 35, so one box in the store up to 35. Again, that would be halfway or 3/4 of the way between 20 and 40. 2 and 55. 55 being 3/4 of the way between 40 and 60. And finally, 3 and 75. The decision we need to make now is, should we or shouldn't we draw a line through it? This tends to be a discrete situation where the number of vitamins in the store, when the order comes in, would be modeled by a discrete situation. But after a discussion in my class today, we decided that this could be continuous, because you could have part of a box in there, because we do have part of a box. If you have 15 out of 20, you have a part of a box. So this is pretty ambiguous. It could be either discrete or continuous. But we considered it to be continuous in my class today, so that's what we're going to go with. So we need to draw a line through it, indicating that this pattern continues on forever. Example 2T, analyzing linear graphs. Students in the 9th grade class drew the following graph to represent how much money would be in the class fund after selling sets of photos of their year's activities. Question A, what does the slope and the y-intercept of the graph mean for the given situation? Well, the given situation in the graph is the number of sets of photos sold, and over here, they didn't label it, but it should have been labeled. It should be labeled money in the fund. That should be a dollar sign there. This should be labeled money in the fund. And to really understand a graph, all the labels should be in place. So we're comparing the number of sets of photos sold basically to the number of money in the fund. So to interpret what that y-intercept means, that y-intercept being right here, that means that the money in the fund to start at 0, when they've sold no sets of photos, is going to be whatever that value is. Now, with some scrutiny, I determined that that value is 25. But to answer the question, what does the y-intercept mean? The y-intercept means starting money in the fund. That's what that y-intercept means. Now let's address what the slope means. What does the slope mean for the given situation? Well, what the slope means is we're increasing by the cost of one set of photos. Whatever this increase is, since each horizontal move or move to the left is an increase of 1, we're plotting how much money is in the fund versus how many numbers of sets of photos they sold. So since each move to the right is 1 along the independent axis, or the number of photos, the slope is giving us the cost for one set of photos. That's what the y, or the slope means. The slope means the cost for one set of photos. Part B, if the graph had the same slope but a y-intercept of 40, what can we conclude? So we're saying the y-intercept is moving up to here. As we discussed in part A, the y-intercept represents the starting money in the fund. So if it had a y-intercept of 40, the money in the fund, or the money that is in the fund already, is $40. So the starting value of the fund is $40. Coming down to question C, if the graph had a slope of 12.5, what could we conclude, or what could you conclude? Well, the slope, remember, it's the change in the y direction. That's what that triangle means. It's the Greek letter delta, and it means change in, over the change in the x direction. So if it had a slope of 12.5, that means it'd be going up $12.5, or $12.50 for every photo sold, or every photo set sold. So what we can conclude is that the cost of one set of photos is $12.50. This has been Mr. Pilarski on analyzing and interpreting linear graphs and equations. Thanks for watching. Bye-bye.